Welcome everyone on Zoom and on YouTube Live. I'm David Bader, and I'm a distinguished professor in the Department of Computer Science at New Jersey Institute of Technology, or NJIT, where I also direct the new Institute for Data Science. I'm pleased that you're going to join us today for our inaugural NJIT Data Science Seminar Series. We have a spectacular set of speakers who are data science thought leaders in academia and industry lined up for you this semester every Wednesday at 4 p.m. You can join through Eventbrite and register for our free Wednesday seminars, or you could watch us on YouTube Live. I encourage you also to follow us on Eventbrite. We have an organization and you can follow the talks there, and also subscribe to our YouTube channel. Today, I'm pleased to announce our inaugural speaker, Dr. Senjuti Basu. She is an assistant professor of computer science at New Jersey Institute of Technology. She's recently received the NSF Career Award, and her research on human-in-the-loop systems has been funded by NSF, the Office of Naval Research, NIH, and Microsoft Research. She served as a mentorship co-chair of SIGMOD 2018, and also as the Ph.D. workshop co-chair of VLDB 2018. And currently she's the co-chair of the IEEE workshop on human-in-the-loop methods and human-machine collaboration in big data. So I'm very pleased to have our first speaker here for the series, and I'll turn it now over to Senjuti. For those of you who are on Zoom, you will be able to ask questions through the chat. So you can type your questions there, and about 10 minutes before the hour, we will switch and I'll try to relay those questions that come in to Senjuti. So without further ado, let me switch slides, and Senjuti, you should be able to share your screen now.
Thank you, David. Thanks, everyone, and good afternoon. This is Senjuti from the Computer Science Department. It's great to kickstart the semester with this talk. And this talk is going to focus on one of my major research areas these days. This is the overview of my talk, and please feel free to pause me if there is a question, especially among the students that need a resolution. I also have a vested interest to accomplish, especially for my student audience. I'm here to debunk two myths. The first myth is data science is all about AI. And the second myth is AI is all about deep learning. So I'll show you some of our work, which will hopefully convince you that both of these goes further away from, data sciences goes beyond AI, and AI goes beyond deep learning. And this is especially interesting because I just have taught my first class, Introduction to Data Science, and when the students were introducing themselves, many of them said they want to learn deep learning in data science. All right, so I will start the talk by describing data analytics process. And conceptually speaking, a data analytics process could be described by the following layers. The bottommost layer is data that is being generated or needed by a myriad of applications, from image recognition to decision making. They vary in complexity, need, and nature. The applications attempt to solve problems. That is, they have needs. These needs, the goals, are oftentimes possible to be described succinctly through a function. Some other time, they cannot be. For example, a product design goal may be hard to describe functionally. Contrarily, a query processing goal, such as obtaining top key item, may be easier to describe functionally. Nevertheless, data is large, voluminous, and heterogeneous. They are processed as batch or coming in a streaming fashion. Then, the second layer of this process are models. These models functionally describe the relationship between the data and the goal, sometimes the final goal or some intermediate goals. Then comes the algorithm. There exist machine or algorithms that are designed to solve the problems. And this is sort of the traditional scaffolding of a data analytics system. When humans are mixed in the loop, they sort of are present in the middle. They range in the varied experience and expertise from lay workers such as crowd workers to domain experts. They are both producer and consumer of data. As an example, human produces insights to the data and model, consumes the output generated by the algorithm, and the loop repeats. So this, in my mind, is a human in the loop data analytics process. Now, I want to briefly describe what are the overarching challenges of such human in the loop processes, especially considering the key stakeholders. According to my understanding, one of the most important stakeholders in a human in the loop system is the data. The raw data comes with the challenge of scale, noise, volume, and velocity. And after that, there exist challenges with applications. The applications want to attain high quality, needs to be terminated fast, and of course, the resource utilization, monetary or otherwise, must be small. So these are the need of the applications. Then the next entity in the process are the worker. The worker have their own goals. Sometimes they want to make money. Sometimes they want to satisfy themselves with some other altruistic motivation, such as autonomy or learning, and so on. And finally, there exists platform where the interaction between the human and the algorithms take place. The platforms are many times profit-based. Nevertheless, they want as many applications to get executed and by maximizing throughput, or they want to retain workers or maximizes their revenue. So these are the different goals of the different stakeholders in the platform. The challenge, therefore, is to develop models and algorithms that can strike balance between these conflicting needs and entities. That, in a nutshell, is the focus of my research. Now, describing these overarching challenges in terms of my current projects, I want to briefly mention of the active projects that are currently funded. The first one is designed from the context of the platform. This project focuses on developing middle layer on crowdsourcing platforms, which are popular marketplace to deploy tasks that require human involvement. Such platforms, the tasks are deployed and the humans sign in to this platform and complete this task. And if these tasks are completed satisfactorily, the workers get paid. To date, the task deployment process remains to be painstakingly manual, as there is no help for requesters in deciding how to organize the workforce, in what style and in what structure to satisfy deployment parameters. Consequently, requesters and workers are mostly confined to one platform, as there is no easy portability of deploying process across platforms. The goal of this project is to design a middle layer that sits between multiple stakeholders in a crowdsourcing system to aid requesters in deploying tasks by allowing easy and flexible specification of deployment constraints and goals, and then recommending deployment strategy based on the specification. We'll do a deep dive on some of the aspects of the projects in a few minutes. The next active project that we are working on is similar in nature, but that is more on a hardcore data science aligned. This project is designed to facilitate feature engineering, which we call as attribute design. Attribute design is a fundamentally challenging task, and it requires intellectual output and so on. Although those who practice deep learning, they will say that deep learning will brute force all the features, hence feature engineering through domain experts or human workers are not needed. So our argument in this project is actually to take a middle layer, which plans to strike a balance between a fully automated feature engineering process versus a fully manual feature engineering process. In fact, what we intend to do is to scale up the feature engineering process by involving amateur workers, as opposed to more expensive domain scientists or domain experts. And in this project, we develop a suite of algorithms and techniques for understanding the opportunities and challenges of involving an ensemble of human workers in attribute design, which is inspired somewhat by the ensemble methods in machine learning. The third project, which is designed by keeping the human aspect more in the mind, is it is an optimized human machine intelligence framework for classification. And we propose a computational framework that derives its principles by appropriately combining active learning and human factors modeling strategies to judiciously select tasks and workers for single and multi-labels classification problems. So I want to pause here for a second and justify the keyword I just used as human factors. So this project is slight digression from some of my fully computational projects. In fact, here, what we try to embed is incorporate is some psychological aspects of humans, which we feel are crucial to gain human benefit, platform benefit, algorithms benefit, and the overall holistic health of the system. And finally, the last project is on human AI agile symbiosis. And here at the NJIT side, we are working on developing an adaptive distributed context-aware semi-supervised team decision-making framework for decision-making on naval application. And if time permits, I should be able to show you guys some demos of the system that we have developed. Now, based on these active projects, if I am to summarize what kind of results this project has come up with, the research results of our recent projects have given rise to models and algorithms. And these are some of the venues where these research results are published. These venues are primarily data management or data mining venues. We also have been looking at problems that study workers and their satisfaction, primarily looking at the worker-centric aspect, while not impacting the goal of the applications. However, very recently, I have started looking at the aspect of the platforms. That is, what could be done on the platform that benefits the platform while also satisfying the goal of the entire ecosystem. As well as some of the research results have also come up with system and demonstration in the leading conferences and journals. Last but not the least, I want to very quickly describe how these problems are solved. Many of these problems are solved with discrete optimization technique, especially constraint optimization, multi-objective optimization. I will also deep dive on one of the works that actually use geometric techniques, in fact, computational geometric techniques to solve one of the problems. Of course, we also have leveraged data mining techniques or have designed data mining solutions as well as more AI-based solutions. Now, I will segue to something more specific, especially understanding the role of online web platforms and what are the optimization challenges and opportunities in the context of using the platforms as a destination to work. Here are some of the examples of such platforms that work as a conduit to find both physical and virtual work. As an example, TaskRabbit is an American online and mobile marketplace that matches freelance labor with local demand, allowing consumers to find immediate help with everyday tasks, including cleaning, moving, delivery, and handyman work. Contrarily, Amazon Mechanical Turk is a fully virtual marketplace that allows a fully decentralized pool of human workers around the world to come online and complete tasks and earn small remuneration. So my technical deep dive today will be on a platform. In fact, understanding this platform-centric optimization while also taking care of some of the applications and worker centricity. In particular, I'll discuss some of the recent research results that got published in ICD and SIGMOD this year with my PhD student Dong and one of my collaborators, long-term collaborator, Sihan. So the deep dive on today's talk is going to focus on task deployment recommendation on crowdsourcing platform. So just to introduce everybody to crowdsourcing, it is a process of obtaining needed services, ideas, or content by soliciting contribution from a large group of people. Crowdsourcing systems are built on private or public platforms and are a popular means of deploying a variety of tasks that require human intelligence. In a typical environment, there are requesters. The requesters comes to the platform with some request. That means they need they need to deploy some task for which they need human cognizance. The tasks get deployed on the platform. Workers take this task, they get these assignments, they work on the assignments, and the assignments are finally reviewed by the requesters. And after the review, they either get approved or rejected. And if they get approved, the workers get paid. And that's how the business model runs. Specifically, requesters in a task deployment environment of crowdsourcing log into this platform with tasks that are to be deployed and want to achieve accuracy, certain accuracy, latency, and cost. And it consists of the following pipeline. The strategy design box, the first box, the strategy design box, whose goal is to figure out how many workers are needed, how to leverage the workforce, and in what fashion. Following which, the workers are recruited to complete the task. The workers complete on the task and the results get validated or aggregated. So currently, this entire loop or the pipeline of task deployment is mostly manual, especially the strategy design step, which is where the task designer has to manually figure out how many workers to pick up, how to leverage them, and what fashion. So our goal in this project is to automate some of this manually rigorous step. To summarize what a deployment strategy is, a deployment strategy is a plan on how to carry out a crowdsourcing task to achieve a requested outcome. And we believe that a strategy has 3 dimensions. One is on workforce organization. The workforce can work collaboratively or independently. Second is on work style. It could be only human or human and machine. And finally is the work structure. Either they are sequential or simultaneous. Those in the audience who are aware of data query planning, they may relate this to query planning problem. In fact, what I want to emphasize here is even though there are only 3 axes or dimensions to the problem, and there are few options under each of these 3 dimensions can actually be incorporated in a plan multiple times. In fact, technically, infinite number of times. Therefore, how to design a strategy for a deployed task is not an obvious problem. As an example, so when, as you can see that in this slide, there are 2 figures that enlist that some text have to be translated from English to French, and there are more than one ways of doing it. The leftmost one, which I named as sequential, independent, and crowd, means the workers work sequentially. So worker 1, worker 2, followed by worker n, independently. They don't collaborate with each other, and crowd. And the entire translation is done by human workers only. This is an example strategy. As opposed to that, on the right side of this slide, there is an alternative strategy I call as simultaneous, collaborative, and crowd. The main difference between this and the rightmost one is here, the workers are working parallelly and collaboratively. So worker 1 to worker n are working simultaneously and collaboratively, and their completed task is evaluated and the final output is achieved. So basically the point that comes down to is that given a many number of strategies, how do you decide the best strategy for a set of tasks, and how you can select that automatically and recommend that to the task designer? That in a nutshell is the problem that we are trying to solve. Formally speaking, so let me formally describe the task deployment challenges a bit more. So the first task deployment challenge is that there exist many types of tasks, and those who are aware of these platforms, they know that right now there doesn't exist any facility for anybody to tweak the static form that these platforms provide. And the static forms design doesn't allow the task designer to specify their needs very succinctly. And also they do not allow or help the task designer to figure out how to design strategies so that they can achieve what they're looking for. And we believe that our work is one of the first ever formal contribution towards that state. Specifically, we make the following contribution in this work. We describe how to express deployment strategies as a function of worker availability. As described in the figure, for the same English translation task, there could be different strategies to accomplish it. More importantly, from the perspective of a platform, it has to deal with multiple such incoming requests. At the same time, because of the fact that platform may not have enough resources to satisfy all these requests at the same time, we study the batch recommendation problem. The batch recommendation problem is designed to optimize some platform-centric goals to satisfy a batch of deployment requests. And we will see in a minute what kind of optimization criteria we consider there. For the request that cannot be satisfied as is, we study an alternative problem. We call that ADPAR, Alternative Deployment Parameters Recommendation Problem. And basically the idea is the task that cannot be satisfied as is, we interact with the task designer in an interactive dialogue and recommend an alternative deployment parameters to them until they are satisfied. We present principled algorithms and validate this solution experimentally, and that is our final contribution in this project. So this is the proposed framework. Consider at the very leftmost of this left part of the slide, there are M deployment requests that are submitted to the platform. Each request contains deployment parameters. We'll see them more formally. Each platform also has an available pool of workers which are qualified and ready to undertake this task. We assume that the worker availability is known to the platform. These are the inputs of the aggregator module. And this module consults with the batch deployment module to recommend multiple deployment strategies to this M deployment request. If all requests cannot be satisfied as is, then the aggregator module consults with the ADPAR module to recommend an alternative deployment parameters. So just like a search engine, which sometimes wants to interactively recommend things to user, the ADPAR actually interactively recommends alternative deployment parameters to the task designer. Now, functionally speaking, StratRec contains the following step. First, a set of M incoming deployment requests come to the platform, each with its own deployment parameters. For example, D1 is a deployment that consists of annotation task, and the deployment parameters are described as the deployment is to satisfy the quality to be 80% as if it's done by experts, spending less than $200 within 5 days. This is the deployment request. We call them deployment parameters. These requests are consumed as inputs, and the aggregator consults with the strategy database. This is a strategy database where we have some unique strategies to find out a finite set S of suitable strategies for these M requests. The worker availability is consumed as a probability distribution function, and the strategy modeling module functionally describe if request D deployed using strategy S, what would be its estimated quality, estimated cost, and estimated latency, given worker availability and the tasks. These estimations are the output of the strategy modeling box, and they are submitted to the workforce requirement module. Since the goal is to recommend multiple deployment strategies to these M requests, Then the next module in action is the workforce requirement module that does an aggregation over all this request. Now, finally, the batch deployment recommendation module is the optimization-driven framework that is designed to optimize some platform-driven criteria, in this case, throughput and revenue for the platform, because we are talking about platform centricity, while satisfying task designers' conditions described through deployment parameters. A deployment request is satisfied if there are case strategies that satisfy deployment parameters. Otherwise, it goes to the at-par module, which recommends alternative deployment. For the constraint of time, in the next few minutes, I will quickly focus on this at-par module because it has some interesting algorithmic contribution. So the at-par module, as I showed you, basically engages with the task designer in an interactive dialogue. In this case, the at-par module is suggesting to increase the cost by 2% and decrease the quality by 1% so that for this incoming deployment request D1. So formally speaking, the input to an at-par module is a deployment parameter, D, a set of strategies, a worker availability W, and a cardinality constraint K. And the output is an alternative deployment parameter D prime and associated K strategies, such that at-par is defined as an optimization problem, such that the Euclidean distance between D and D prime is minimized. So we want to minimize the overall cost of latency, the overall difference between the cost, latency, and quality, while satisfying these constraints such that we can get case strategies. So as an example, out of 3 deployment requests, D2 came to at-par with the following deployment parameters. It wants to achieve 80% quality and spending 0.2 cost and in a latency of 0.28. Don't get intrigued by these fractions. Basically, what we have done here is that we have normalized the actual values so that they all belong within certain range of 0 and 1. Now, worker availability is captured as a probability distribution function by leveraging historical data on a platform. For example, the PDF can capture there is a 70% chance of having 7% of the workers and 30% of chance of having 2% of the workers available who are suitable to undertake that task. In expectation, this gives 5.5% of available workers. If a platform has 4,000 total workers to undertake certain type of task, that gives rise to a total of 220 available workers. So StratRec, our proposed framework, expects such expected values as inputs. On the contrary, there are 4 strategies that came from the strategy database, and the strategy modeling module has estimated the quality, cost, and latency of these strategies based on the worker availability W for the deployment parameters D2. Our solution for these at-par problem is actually geometric, and it exploits the monotonicity of our objective function. So I'll try to go a little fast, and during the question answering time session, I will answer specific question if you have more. In fact, what it does, it actually employs a computational geometry-based solution to provide an exact solution for this alternative deployment parameter recommendation problem. This computational paradigm is known as sweep line paradigm. The idea is to imagine that a line, often a vertical line, is swept or moved across the plane. So please note that we are operating on plane. Stopping at points, geometric operations are restricted to geometric objects that are either intersect or in the immediate vicinity of the sweep line. For our problem, the geometric objects are the strategies that are defined by a point in a 3 dimension. And the main intuition is that to be able to produce an alternative deployment parameter D prime, it must cover at least case strategies on quality, cost, and latency. The sweep lines must advance appropriately in each of these dimension of quality, cost, and latency so that it gets K strategies, and the increase in each of this dimension or relaxation is minimal. So to solve this problem, our proposed algorithm at per exact first normalizes quality cost latency thresholds of a deployment of a strategy uh, within a normalized range and inverse quality to 1 minus quality. This step is just for unification, making our treatment for all parameters uniform inside at par, where smaller is better and the deployment thresholds are considered as upper bounds. With this, each strategy is a point in a three-dimensional space, and a deployment parameter is an axis parallel rectangle in that space. So the red box is the deployment parameter, which is the axis parallel hyperrectangle, and these are the strategies which are points in this three-dimensional space. The first step is to actually compute the required relaxation needed for each parameter between the strategy and the deployment request. The next few steps, which are more involved and basically describes the algorithms in details, relies on designing some data structures and figuring out how we would move the sweep lines along different planes and in what amount, so that we can capture a relaxation by making the smallest increase in our objective function while satisfying the constraint of getting exactly case strategies. So that in nutshell is the essence of at par exact algorithm. I think I'm going to skip the details because it might be too involved, and people who are not familiar with computational geometry, it might appear too hand wavy to them. But I'm happy to answer questions. I have the details on the slide. I'm happy to answer questions if there are anything specific. So the point is, this algorithm, what we show theoretically in our papers, is that it produces the tightest relaxation, meaning this algorithm is an exact algorithm. And the running time is dominated by the number of strategies and dimension of the deployment parameters. So for more results and more details of how exactly these techniques are designed and developed, I would like to refer you all to the papers, Sigma 2020 paper and the ICD 2020 paper. Now comes perhaps the more interesting part. So we also conducted experiments. And so the experiments are actually divided in two parts. One is the real data experiments, which was conducted on real crowdsourcing platforms, and the other are synthetic experiments. So the real experiments, real data experiments, are designed on sentence translation tasks and text creation tasks. So these are real tasks that were deployed on Mechanical Turk, which is a real crowdsourcing platform. So the main goal of these experiments were the following. The first question we asked through this experimentation is, can worker availability be estimated and does it vary over time? For that, we performed 3 different deployments for each task at different time of the week. And the long story short, we realized through this experimentation that worker availability can be computed and it does vary over time. The second question that we asked through this experimentation is, how does worker availability impact deployment parameters? So we need to be able to calculate the quality cost latency along with worker availability. The quality and the latency, the latency and the cost are easier to calculate. Basically, it's the total amount of money that was paid to the workers and the total amount of time the workers used to make edits in the document. And our experimental results show that worker availability actually linearly, at least for those tasks that we deployed on Mechanical Turk, worker availability linearly impact those parameters. And finally, the most important question that we validated through experimentation is strategy recommendation useful? Basically, what we did is that we deployed our framework on the platform and compared with the default Mechanical Turk deployment processes. And we ask workers questions in terms of their satisfaction, as well as we also have measured some quantifiable entities such as time, quality, etc. And our results observe that deployments using StratRec achieves higher quality and lower latency under the fixed cost threshold on an average compared to the deployments that is there by default in Amazon Mechanical Turk. So these experiments, to some extent, validates that what we are proposing has some merits to the community. Now, showing some of them with figures. So the first figures show with statistical significance, deployments using StratRec achieves higher quality and lower latency under the fixed cost threshold on an average compared to the deployments that do not consult StratRec. The second picture shows that worker availability varies over time. Now, briefly talking about our synthetic data experiments. The synthetic data experiments are designed to basically validate our algorithmic aspects and the scalability of our proposed solution. So there we vary the number of deployment recommendation, number of strategies, worker availability, batch size, and different distribution of the task in the batch size. And we have implemented different solutions to compare ourselves with baselines. At this point, I also want to note that there doesn't exist any prior work on this. So the closest to our work is probably query relaxation strategies, those who are familiar with database literature. And we actually did modify some of the query relaxation strategies to adapt to solve work as a baseline problem for our problems, for our settings. Our experimental results showcases that at per exact or produced solutions returns the exact solutions to that per problem and significantly outperform baselines. It also shows that it is scalable and takes a few seconds to return alternative deployment parameters, even when the total number of strategies are large and the value of K is sizable. So in summary, this project is the first ever work that proposed a framework to recommend deployment strategies in crowdsourcing platforms. It presents principal models and algorithms with theoretical guarantees and present rigorous real-world and synthetic experimental results. So this is one of the deep dive that I wanted to show, and I wanted to show this work to convince at least some of my student audience that you can do data science without directly doing AI. So basically the solutions that are used in this project, at least for the problems that I have described, are geometric techniques and discrete optimization techniques with guarantees. Now, those who are already bored with my lambda, theta, and sweep lines, I want to take a quick detour, and I want to talk about a more fun project and my champion students who have been doing a fantastic job in this project. So this detour is to convince you that AI is not all about deep learning. So this is more of a traditional AI problem, and we have an interesting take on how to solve this problem. And this is the part of a Office of Naval Research project that is currently funded by them. So this is the problem that we are solving there. Our goal is to navigate in cooperative ships, we call them agents, with different starting points over a discrete grid to discover an initially unknown destination. And this is a very practical and highly relevant problem for Navy folks, because when there are, they call them as resources, and they want to find these resources or assets in the ocean, sometimes, most of the time in a cooperative manner. And while basically while the ships are working on their own, they are also making sure that they are working towards a common goal of discovering the asset by satisfying some constraint and optimizing some goals. So again, this is a problem. This is again an optimization, a constraint optimization problem. In fact, it's a multi-objective constraint optimization problem where we want to navigate these and cooperative agents over a discrete grid by minimizing total time and total fuel consumption while avoiding collision. So the first two points in the objective and the constraints are the objectives, and the final one is a hard constraint. You must avoid collision between the ships. So this problem, we actually formalize this problem as a discrete Markov decision process problem. And we have a state space. The size of the state space is actually pretty large. It is the size of the grid to the power n, where n is the number of agents. And basically, we are talking about a synchronous decision making of the n ships, where a state is defined by the position of the n ships at a given point in time. And this problem, this discrete MDP basically has the goals of which are the objectives, and we have basically this different reward function that are expressed with different reward function. One is the exploration reward, which simply says that since that destination is initially unknown and the agents do not get to see the entire grid at the same time, so the exploration reward simply quantifies how much of the unknown grid at a given point in time an agent can see. Similarly, the fuel and the time reward actually quantifies how much of fuel consumption and the time, unit time, and the progress towards the goal an agent will make in a unit time. So the further details are not there in the slide, but the point that I want to make is that we realize that even though we formalize this as a discrete MDP, the reward function is not easily differentiable. So we actually solve this as a reinforcement learning problem. So those who, and especially the students who are not aware of reinforcement learning is an area of artificial intelligence on how agents have to take actions in an environment in order to maximize some cumulative reward. It's a basic paradigm of machine learning, which is neither supervised nor unsupervised. So my students have come up with this model, teammate model of, it's actually a multi-objective reinforcement learning problem where we have shown that how this problem could be solved with three components of reinforcement learning using the teammate model, action selection model, and the learning model. And I can definitely give further details while in the process of making submissions during the question answer section. So finally, and this is probably the most cool part of the presentation, this is a demo that Satya, one of my master student, has developed, in fact, within a week. So this is an operationalization of the process. You can see there are 9 ships, and this is the real grid. I think this grid has been taken from Miami. I don't fully remember, but this is the real grid that has been discretized. And there are 9 ships. The ships are all looking for this red dot, which is unknown in the beginning. And this demo will show that how these ships will cooperatively navigate and all finally reach the destination by minimizing the fuel consumption, the overall fuel consumption, and the time. So I'll start the demo now. So this is the demo. And the point to note here is that this actually, the demonstration that I'm showing you here, it's actually just not the reinforcement learning. It's actually an approximation of some of the parts of reinforcement learning, because when we are dealing with 9 ships, the state space size is huge and humongous, and we were dealing with the problem of how to store these state space. So it's an approximation of the actual state space of RL model. And the second point I want to make here is that the 9 ships, they have different velocity, and of course, each of the ship has a maximum velocity. So the question is also, at a given point, a ship can wait or a ship can move in its maximum velocity or any velocity smaller than the maximum velocity. And this demo shows that how they should navigate in the environment to find out this unknown destination by minimizing the overall time and the fuel consumption. So that's it, I guess. And it looks like I'm on time. So I want to give a shout out to my amazing crew and my lab, my PhD students, master students, and BA students who have never failed short to live up to my expectation. And I'm a pretty demanding advisor. So thank you for listening, and thank you for all my funding agency for funding all these fun projects. So I'll stop here.
Thank you very much, Senjuti. What a great talk. And I was really blown away by the work that you've done and these innovative deployment strategies for crowdsourcing that I hadn't seen before. There's a question on the chat right now from Baruch, who asks, in the exploration problem, do you know the grid in advance, or do you discover it as you explore the environment?
We do not know the grid in advance. We explore the environment on the go. So basically what we are, and some of these details are not in the slide. So basically we are assuming a sensing radius, a fixed sensing radius for each of the agent. At a given point in time, the agent can only see the grid up to its sensing radius and not beyond. So the entire grid is not known. The grid is discovered on the go. But at a given point in time, you remember all the things that you have seen in the past and new things up to the sensing radius.
And Baruch asked another question. What if the objective is that just one ship reaches the goal? Does anything change?
So if one ship reaches the goal, well, we can also implement. I mean, I wonder what exactly Baruch mean by that. But if it means that the solution or the model needs to change or not, I think the problem can still be solved as an MDP. It could be modeled as an MDP. Basically, the goal will be to figure out the next move of the ship. Of course, the problem will become easier because there is no notion of collision there. So the ships can always move at the highest velocity. So the hurdles that we are solving in this problem is we have to figure out at a given point in time, so at a given state, what are the action of the ships? The action of the ships is to move in any velocity less than their maximum velocity or weight. And so when there is only one ship, the problem actually becomes much easier because your action space is also smaller.
So if there are those on Zoom who have questions, please type them into the chat. Maybe Senjuti, I can ask you a question about the deployment strategies where you're looking at using these workers. Do you maintain any history of the workers, or is every worker fresh and new in the optimization?
So it's an interesting question. So actually, we do maintain a history of the workers, not yet in the published work, but we are working on a follow-up work where we are maintaining the history of the workers to find similarity of worker availability based on the type of tasks they do, their demographic, and so on. In fact, we had a demo in Sigma 2019, 18 maybe, where we did show that how we can get to know about workers by looking at their history and the similarity of their activities and some other socio-demographic evidences.
So many of the folks on Zoom and in the audience know about using Amazon's Mechanical Turk for crowdsourcing. Have you noticed any difference pre and post pandemic? Has there been any change in the types of uses or how people are using crowdsourcing?
So here is the thing. I think I spent $900 in last 4 months in Mechanical Turk. So that's a lot of money for Mechanical Turk, because typically you spend in cents, I mean, few cents. But I was told those who were involved in the experiment design, I actually spent $900 on 2 different papers. So I believe that workers are more available. That's my gut feeling. But I will have to be honest that I did not spend a lot of time myself on Mechanical Turk recently, but I got to see results pretty fast. So my feeling is that this micro gigs actually matter these days, especially for countries where a few cents actually is not a very small money.
That's great. Do you see crowdsourcing changing in terms of how it's used going forward now that it's deployed widely and so readily available, and with new strategies that you've developed? Do you see a new type of use for crowdsourcing?
I have been seeing I have stopped using the word crowdsourcing quite intentionally, and I say more of human in the loop processes, because I see such a pervasive use of that paradigm in many applications, as much as even ecological applications. In fact, one of my NSF project is to actually deploy this framework on iNaturalist. So iNaturalist is an ecological data platform. It's hosted by California Academy of Sciences, and my collaborator from there. Our goal is to basically deploy this recommendation strategies on the platforms, and the platforms they're not really crowdsourced workers; they are citizen scientists and or naturalist, and the goal is how we can make more meaningful recommendation to these citizen scientists, so that they learn things, in turn they contribute more effectively to the platform. Yeah, so I do see a pervasiveness of human in the loop processes, and I do see a real shift of how crowdsourcing has been used traditionally and how it has changed.
Sure. It reminds me, on social media, I typically see posts from friends like, this new type of mushroom grew on my property. Is it edible or not? So
Yeah.
you'd like your friends to be able to identify it before you eat something deadly. But
Right.
I've also seen posts like, I got bit by this snake, here's a picture of it.
Oh my
Where
God.
you want to have a response from your friends that's accurate and fast, and
Right.
maybe you'd be willing to have a human in the loop to have some of those answers faster.
Right.
So thank you, Senjuti. Again, congratulations for receiving the NSF Career Award. That's a fantastic honor, and I'm pleased that you're our inaugural speaker in the Data Science Seminar Series. We look forward to joining everyone next week, Wednesday at 4 p.m. Eastern on Zoom. And also, you can like our channel on YouTube, where we're going to live stream. So thank you again. Thank you, everyone, for participating in our seminar series, and we'll see you again next week. Thank you.
Thank you, everyone. Thank you, David, for inviting me. It's been fun. Thank you.
Bye-bye.
Bye.